Hello and welcome to my presentation on Unary 1 cancer problems. I'm Henry and I hope you enjoy my short presentation. Just a little bit about me. I'm a first year PhD student supervised by Dimitri and Marcin. I came here from Warwick after finishing 3 years of my discrete maths degree. And generally speaking, probably why I'm here, my interests involve automata, complexity and logic. And I guess here's some of my non-PhD interests as well. I am quite into my Formula 1. Anyway, deterministic finite automata. I hope you've got at least a distant memory of DFAs. We say a transition read the letter that it's labelled with, and that red letters are strung together to form words. And if we start from the designated starting state, as you can see here, for example, we read the word ABB before reaching this kind of distinguished double-lined final state. We can then say that ABB is in the language of the automata, here denoted by L. Okay, let's take this one step further to NFAs. Roughly speaking, non-determinism allows for kind of choice. Whenever there's two or more outgoing transitions with the same label, or one of these special epsilon marked transitions, we can choose to take whichever we like. So, as you can see, if we're at the top right state and we want to read 1A, if we choose to take the epsilon transition, we can go to this final state and then take the transition to the rightmost state, or we could start at the top left state and immediately read the A and end up at the top leftmost state. Again, if we take the topmost branch, we can see that we read A, B, and epsilon, but somehow epsilons count for like null letters, so we can kind of crimp them out of the word that we read. And here we can say that the word A, B is in the language of the automata. Okay, again, one step further, we go to unary NFAs. You can see here these orange marked A's were originally B's. I've kind of relabeled them and let's kind of bring them back to normality in green. And we can see now that the only change is that the alphabet is singleton. Just the letter A can be read. So all words of the form sort of A, etc. Okay, and if we take the top branch again, we can see that we read A epsilon, so we say that AA, or maybe more succinctly, A to the 2 is in the language of the automata. Okay, now finally I can kind of define 1 counter nets, or at least unary 1 counter nets. So imagine just combining a unary NFA and a non-negative integer counter. You can see these kind of integer updates in red below the transitions. They represent kind of updating the counter. Now, we need to now keep track of a state and a counter value, right? And we can kind of call this pair configuration. We say that the starting configuration is, well, the starting state and the counter value 0. And we can see that, well, the counter value 0 at the top there starts at 0 and has this crash condition. So if we ever go sub-0, the automata kind of immediately crashes and the word that we were reading is kind of instantly rejected. So kind of illegal configurations take the form of some state and a negative integer counter. Also note, if we kind of add or take 0, I might not write this down in this transition just for simplicity, so let's kind of get rid of those two. Okay, now take the previous example again. We start the start state with counter value 0, we then read an A and add 55 to the counter. We then read another A, take 2 from the counter, and then finally we take this epsilon transition, and we still do take the effect of -1 from that update. And we're left with counter value 52, and we can say now that A to the 2 is in the language of the automata. Everything's fine. Okay, now hopefully the model is clear. We can start to ask the sort of natural automata-friendly decision problems. I don't know, for example, we could be given an automata and asked if the language is empty, or maybe we could be given 2 automata and we could ask if the languages accepted by the automata are equal. Such questions are important for verification purposes. You can imagine a unary 1 counternet, which could have accepting runs if and only if some program can reach an error. And querying emptiness would therefore provide confidence whether or not it is possible for the program to ever reach this kind of error condition. And somehow there's this kind of trade-off between capability of automata and the difficulty of such decision problems, where the more capable your automata is, the more likely these decision problems are to be challenging, maybe even undecidable. I guess today I'll speak about 2 or 3 problems: membership, perhaps compressed membership, and universality. I'll move on to those in a moment. Okay, first, universality. Universality takes as input an automata, in this case a unary 1 counternet, curly A, and the question is whether the automata accepts all possible words. In this case, because they're unary, this is all like A to the N. And here's an example, right? It's kind of like the previous one, but slightly simplified. We have this top branch where we can gain some counter and then read some A's and take some counter away, and on the bottom branch we can read as many A's as we like and gain some counter in doing so, but then we kind of have to beat this -100 kind of guarding transition in some sense. Maybe you spotted it quickly. This is a false instance. A to the 99 isn't accepted. it doesn't quite make it on the top branch, you would hit negative counter value, and on the bottom branch you'd want to read at least 100 A's anyway, so that doesn't work. And maybe this could become quite trickier for larger examples. In this case, 89 is the only word not accepted by the automata, so if you were to kind of check non-universality, you would have had to have found this exact word. And you can kind of imagine this is maybe not so easy in general, and the complexity maybe reflects this. This is CoNP hard from Unary NFA, universality, and has been recently shown to be inside CoNP to the NP with some clever guessing and checking. And so if 8 to the 99 was of interest, maybe its membership generally is of interest. So we have a Unary 1 counternet as input, and a word, and I know the format of the word is going to be some sort of string of A's. And the question is whether W belongs to the language of the automata. If we take the previous example and we query whether the word a 5 A's is accepted by the automata. And this is kind of fine, right? We take the top branch, we gain 98 counter value, and then we use this little self loop on the accepting state 5 times. Everything's fine. But then what if we wanted to query whether 8 to the 99 was in the language, just like last time? It seems interesting to us. Well, we could write this down, but somehow 8 to the 99 ends up being extremely long. I don't have enough slide to fit it on. This seems impractical, and really there's a problem. It's not really with the word that we asked, it's not really with the automata as an example, it's really with the encoding in the input question. We have unary input for a unary word. It seems inefficient. We can improve this to compressed membership. Rather than inputting the word directly, we input the number of A's we want to read, and we ask whether A to the n is in the language of the automata. It's the same thing, but kind of crucially, we input the number n in binary, right? The bit size of n is equal to the log n. This is compression. So now the example is much more succinct. I can really fit it on my slide there. You can see W equals 8 to the 99 on the left-hand side. And we know from previously this is not accepted, but really the question is this problem in P? It's been shown to be NL hard and is shown to be in NP in the same paper that showed the universality was in CoNP to the NP, using some sort of fairly clever guess and check. And it'd be really nice, I'd be very happy if this was in P. Okay, and now I've kind of chalked up the bounds in black, and I kind of open questions, I suppose, in orange. Somehow there are 4, right? I could push the bound to upper or lower in either question of universality or compressed membership, and I don't really mind which, I just kind of want to know. These questions aren't immediately kind of independent. For example, if I showed that compressed membership was in P, then I could get a CoNP bound for universality. I could just guess the non-member and then check it using my polynomial time compressed membership algorithm. That'd be great. And recently it was shown in Concur 20 that there is an NP algorithm for compressed membership, which is great. And then they use that to leverage universalities inside CoNP to the NP. And I guess this shows off the timeliness. They also talked about various other universality problems in not just the specific example I've been talking about today. Okay, I wanted to kind of round off by showing kind of the location of Unary 1 counternet in theoretical computer science. I can show fairly strong connections from two-dimensional vector addition systems with states, semi-linear sets, and various decision problems, maybe specifically unbounded knapsack. And kind of here's the broader space, kind of all the other general places this sits within. And I kind of wanted to highlight one thing, is probably my most important, or my kind of, yeah, I guess my most important observation contribution so far is I can show a very strong relationship between the languages accepted by Unary 1 counternet and a specific type of semi-linear sets. And perhaps I would have needed another 10 minutes to explain in detail what this is about. But thank you very much. Do you have any questions?